Okay, so question one here, classic type of question. This one looks, it should look familiar to the other worksheets just because, it's just like such a popular type of question here. So essentially what we have is these four long straight wires, each at the edge of a square. And we know that it's a square because they all have the same lengths. We know the magnitudes of each current and how they're pointing. So out of the page or into the page. And we want to determine the net magnetic field at point P, which is located at the center of our circle here. So let's draw our square. Kind of quick there. Here are our four little wires here. Now guys, watch this. Bam. That's how it's done. And we know we'll call this I1. I guess sorry, I didn't realize I didn't label them correctly, but I presumed it would be like going clockwise starting from the top left corner. They would have to include the drawing or say otherwise. Or actually that was I4. So let's just use the drawing then instead of talking about it. So I4, this is equal to 1 amp, coming out, I1 down here. It's a 2. 2 over here. This is going into the page, X is going in. It's equal to 1 amp. And then going into the page, I3. 2 amps. Okay, draw a standard coordinates grid here. Put this guy in the middle. Point P. Okay, so at this point we have enough now to kind of set this up. Make sure you're muted if you're just hanging out on the Zoom and don't have a question. We know each side's 1 meter. And now we need to use our right-hand rule number 2. So basically whenever we have a wire that's going like into or out of the page, we know we're gonna have to use that right hand. Oh, I say number 2, but that's basically the one where your thumb points the direction of the current and your fingers curl. Okay, so key to this is you draw the shortest distance between your wire to the point of interest. And in this case, it'd be something like, starting with I1, it'd be something like that, right? And we'll call that distance R. But we don't know what R is, so let's first find that. So we know from here to here, it's 0.5 meters. And it's a square, so from here to here, it's also 0.5 meters. So you can use Pythag to solve for R. R is going to be equal to 0.71. Okay? And now you can use your right-hand rule to determine the direction that the magnetic field is going to go as contributed by that I1 at that point 2. So remember, right-hand rule number 2, our thumb points the direction of the current. It's coming out of the page, so I'm basically doing, like I'm looking straight down at the paper, I'm doing a thumbs up into my own face, and my fingers curl. Now, the direction of the vector is always perpendicular to the shortest distance between them. So shortest distance between our wire and that point of interest, that's this right here. Perpendicular means 90 degrees. Therefore, the only way it can be perpendicular is a vector that points like this, hint, that's the right one, or like this. That's the only way it can be 90 degrees. But how do I know it's this one and not this one? That's where the right-hand rule comes out. So essentially what the right-hand rule tells us the direction the magnetic field is emanating from this point of interest, okay? So it's going to be like this, keeps coming out, this, and then at this point right here, kind of, as I saw there, the vector is pointing upwards. So at that point in space, we have the B vector pointing up like this. So I'll call that B1. And now, we've seen it once. We're going to do this a bunch more times here. We're going to be doing the right-hand rule again, number 2. So basically I say 1 and 2. 1 is when we have this whole situation, with the current's a nice contrast. We have this whole situation, where like the velocity or the direction of current is pointer, middle finger is the direction of B field, and your thumb tells you the direction of the force. And then we have 2, which is this whole situation, like where your finger points the direction of the current and your fingers curl the direction of the B field. So in this case, we draw the shortest distance between these 2 points. Let's draw this. I'll do it in orange this time. Basically, I'm doing a thumbs down into the page, and my fingers curl going clockwise. So it's going to be something like this, right? Going clockwise. It expands out infinitely, right? This is like a huge thing. And at this point, it points like this. Therefore, we'll say B2 is right here. Now we'll use I3. I'm going to kind of go quicker now because the same person has joined the Zoom, left the Zoom a bunch of times. I wonder if they're having tech issues. So you put your thumb going down again, and your fingers curl. In this case, the shortest distance is going to be like this. I don't want to draw over my line. It's like this, and it's going to be emanating going this direction. So over here, we'll say B1 plus B3. And then finally, we're looking at B4, kind of an awkward one, but your thumb's pointing out. So your fingers are going to be curling in a counterclockwise direction. So at this point in space, it's going to be going like this, plus B4. So, we did the hard part here. And from here, it's a smooth sailing vector addition. Let's kind of draw just some axes to make this a little easier. Angle theta here is the same angle theta right here. And we can solve for that angle. With my steps here, I first solve for r. We can solve for that angle using a tan function, but it's going to be 0.5 over 0.5. So it's going to be 45 degrees. It was 45 degrees. And then, from here, it's just, the drill, right? So we have our cosine components and our sine components. Just to be thorough, I'll draw them in. Let me get rid of this here, write it down here. 1 meter, from here to here is 1 meter. We'll say this is B2 sine theta plus B4 sine theta. And this is B2 cosine theta plus B4 cosine theta. And then same idea over here. I'll do this part in red. Sorry, I don't mean to confuse you guys. I just kind of want it to be clear with the colors. Oops, this is 1 and 2. So B1 cosine theta plus B2 cosine theta. And remember, with forces and fields, this is a magnetic field, so it's a vector. So we let the sign based on our coordinate system tell us how we're going to be plugging in. And like I said, B net, this should now be nice and fun and easy. Let's first start with B net X. And I encourage you to, use the SI worksheets because, we just practiced it so much. So it should be like second nature to the people who have been frequently looking at that. Okay, so in our X direction, we have B2 plus B4 cosine theta in the positive direction. And we have B1 and 2 in the negative direction. So that's how I'm getting that. It's minus B3 cosine theta. And then our equation for this is mu naught. I'll write it all out this time, but I think in the next part, just to kind of be snappy, I won't write it all out. And then we're almost done. Okay. And you can just do some factoring, definitely factor here because, there's just so many parts. And all you're left with is an I2 plus I4 minus I1 minus I3. Sorry, bad I. Okay, plug everything in, work this guy all out. And actually, like, the 2 pi cancels out because that mu naught, see message in the chat. Oh yeah. So yeah, that's kind of an advanced tip in the chat. I got a PM saying, can't you put your coordinate system on a slant so you can just kind of do a one and done situation? And yeah, you can do that, but it's a little bit more of like I'm gonna say advanced technique, but you just knowing to look at it from a different way. So I was kind of like, just keep it simple here. But yeah, you can totally do that. And because this is 4 pi times 10 to the minus 7 divided by 2 pi r, these, we can just cancel out like this, call that a 2, cosine theta, and then it's going to be 1 plus 1 minus 2 minus 2. Work this whole thing out, and what you get for the net x direction, let's see if we can chat. No. Is a minus. So we know that we're going to be going the opposite way that we defined as positive. And then 1, 2, 3, 1, 2, 3, 4 t. Do that around every 3 zeros. I do like a little bracket just to be clear for everybody. Okay, b net x, and now b net y, we work out very similarly. So looking at it, everything's going in the positive direction, so they're both pointing up. So it's just going to be adding every single one. So let's see, b2 sine theta plus b4 sine theta plus b1. And then, plug it in, work everything out, factor out where you can, do everything else the same that we just did. And what you'll get is 0.123, 1, 2, 3. Zeros right there. And now we have b net x and b net y. So we can redraw our vectors here. So we have b net x came out as a negative here. So that negative right there tells us that it goes against our coordinate system. We define rightwards as positive. So in this case, b net x is going leftward because it's negative. And then we also have b net y positive, which we defined as up. So b net y. And then b net, what we're looking for in sum, is going to be that vector. And over here, since we have a vector, we're going to need the direction. We'll call that theta prime. Solve for b net through the equation presented up here. That comes out to be equal to 3. And then our angle, we'll just use a tan function. (71.6 degrees), and then we'll call it above the negative x axis. Okay. Okay, I'll pause here and then take questions. I see that we have some questions popping up. Thanks, Samantha. She pointed out that I accidentally wrote down here and down here, I wrote b2, but it's b3, right? Remember, this is the vector that constitutes all of these guys. So yeah. And then in question 3, we have two thin wires that are placed 0.1 meters from one another as shown in the figure. We have, as shown in the figure, we know current 1 and current 2. We want to determine the magnetic field at point A and then also at point B. Okay, so, at A, it's a little bit nicer here. So it's kind of an easier version as before, but I still think worth it. So we have our two wires right here, both of which are coming. Oh, question. Oh, yeah. Point A. Both these guys are coming out of the page. I1 and I2. And we want to, set up our equation here. So let's draw our coordinate system. This is for part A. Okay, so right-hand rule number 2, our fingers emanates out like this. We're here, it's pointing up in this direction, needs to be perpendicular. So we'll say B1 is pointing upwards. And then B2 is pointing downwards, because here, again, our finger's going up, but now we're curling on to the left of it. So it's going this way. So it's like this. Okay. And we just set up our equation. We'll say B net is equal to B. Well, let's work with a positive here. So B2 is bigger than B1. So I'm going to write B2. Well, I guess I should write it the way that my diagram tells me to. B1 minus B2. And you just use your equations here. Over 2 pi, the distance between them, we'll call it x over 2, which is just going to be 0.1 over 2. So x over 2. Oh. 2. And what can we factor out? Well, we can factor out mu naught, 2 pi, and 0.1 over 2 for that matter. Leaving behind I2 minus I1. Sorry, wrote these backwards. And we're going to come out with a value that's going to be pointing down, because it's going to be a negative. I didn't plug into my calculator, but it's going to be equal to, we'll call it x for now. I'll let you guys work with that. But we know it's going to be pointing down because we know B2 is bigger than I1, because I2 is bigger than I1. And then in part B here, we're asked at point P. So, very similar setup to kind of what we just did, but let's draw it out. So we have this triangle. There we go. We're going to have, let's do it in red. Sorry, I'm so bad at these circles here. I1, I2. We're going to call this P, which is where we're going to be looking for things to be acting. And we're going to need to draw this guy out. So let's first start with I1. So we do, our right-hand rule. Number 2, thumbs pointing out, fingers curl, and our B1 vector is going to be sticking out on some angle like this. It's B1. And then with respect to I2, thumb pointing out, it's going to be pointing this way. B2. Okay. And now we need to establish the components of B1 here. So B1 has this angle theta. And then that, by definition, that means this angle is also theta, their ultimate. Well, it's actually the same triangle, right? But a lot of people ask me, like, how do I know when this is theta, this is theta? Like, if you have like a good eye for like 3D space, you'll know if you rotate it 90 degrees downward, like this line right here is this line, and this one is this one. So that's how you know these are the same angles. And a lot of times when you do this vector addition, like that's something that should just be like second nature now. You should know that those are going to be the same angle. Okay, and since this guy has components, we'll say B1 cosine theta, and this is B1 sine theta. Okay, and we know what to do here. Okay, let's start with B net x. That's going to be equal to B1. Actually, let's redo this coordinate system. We can redraw this coordinate system such that we're only dealing with positives. So we'll have x pointing this way and our y the same direction. And all I did was split the direction of x because I know both my vectors are pointing leftwards. So might as well have it pointing this way such that we're dealing with positives. For me, positives are a little bit easier to work with. So we'll say b1 cosine theta plus b2. We should know now how to expand these and plug everything in. But let's first find, well, actually, I should write it out because we have to use some trig here. Theta, and then plus mu naught I 2 over 2 pi y. We'll call this y, call this x, and this r. Okay. So y I give you in the picture is equal to 0.2, x is 0.1, yeah, 0.1 meters. And then you can solve for r using trig. R is going to be equal to 2.2 meters. And then also that angle theta we want to find is going to be equal to tan theta, which is equal to 0.1 over 0.2, opposite over adjacent. And theta comes out to be equal to 26.6 degrees. Okay, so you know what theta is. We know what r is, and we know what y is at this point. You can just factor out to make it look nice. No, just sorry. That I1 over r cosine theta plus I2 over y. Okay, plug in, solve. This part comes out to be equal to 0.00. Is that 5? All right, 5. 7.4 t. And b net y. All we have is just the y component of b1 pointing upwards. So, oops, b1 sine theta, which is going to be equal to mu naught I1 over 2 pi y sine theta. That comes out to be equal to 3, 2, 2, 2, 2. Like this. Okay. And then you know how to solve for b net, just like we did. That comes out to be equal to. Okay. And of course, we need to find the direction. So we have both of our x and y components came out positive. So we define positive in the x direction is this way. So b net x. Y direction is pointing upwards. So we have something like this. We already solved for b net. Let's find this angle alpha. We'll use a tan b net y over b net x. That alpha is equal to 9.3 degrees above the positive x-axis, or how it was defined in our drawing. Okay, so, oh no, what did I do? So, let's pause there and see if there's any questions. Okay, so we have this generated situation where we have a conducting rod of a certain length that is free to slide on the conducting wires. The entire circuit is immersed in a constant uniform magnetic field going into the page with a strength 0.5 T. The wire is pulled to the right with a constant velocity. An EMF is induced in the circuit. We have an expanding loop, so that makes sense. And the circuit has a total resistance of 2 ohms. The first thing we're asked is, in which direction does the flow in current, right? So clockwise or counterclockwise. So we have to use Lenz's law to find this. And this was what tells us, like, it's a kind of a subtle thing, but it's important for us to understand because it really kind of underlies most of these questions. And we know the loop is expanding because the rod is leaving. So it's like becoming bigger on the inside. Like, I saw a confused face on Zoom. So if we have like a loop like this, and we have this rod right here, if I'm pulling the rod this way, the area within here where there's the magnetic field is going to be getting bigger. But don't worry about that now. Let me explain. So it's changing. So Lenz's law tells us when a conductor experiences a change in magnetic field, an an electric current is induced within the conductor, right? And the direction opposes the change in the magnetic field that induces it. So it's basically a statement on the principle of conservation of energy, right? So what's happening here is we're going to have more B field going into the page within our drawing. So if we think about our drawing, it looks like something like this. Here, I'm gonna try to draw this one neat over here, because I think it's kind of the hardest topic, in my opinion, for this section. So we have our loop, and we have our rod. Let's do it in blue. That's a good rod. Sorry, still getting used to the iPad. There's a way to make rectangles. Oh my God. All right, here's our and here's our rod that's getting pulled to the right with a velocity v, right? It's getting pulled this way. And within this area is this B field that's going into the page, right? There's a bunch of them. And there's more over here too. So as the rod continually moves to the right, there's going to be an increased amount of B field going in. So by that principle of the conservation of energy, we need to have a current that produces a magnetic field that opposes that change, right? So if we think in terms of right-hand rule number 2, I kind of taught you guys 2 ways to do this. You can either memorize the table that we talked about during SI, or you can kind of think about it logically, like how I'm describing. Okay, so we're going to have an increased amount going in. To oppose that, we're going to need to have more B field coming out. So if you think about our right-hand rule number 2, and let's put it at any point along the current here. Well, here's the hint, it's going counterclockwise. The only way to have more going out is if your thumb, let's talk about the wire, or I'm sorry, the rod here. So your thumb is pointing northward with respect to the plane that is your paper. Your fingers are pointing out of the page. It is only when you are moving counterclockwise will your fingers be curling out of the page. And again, that's going to oppose the direction there. And then the other way you can think about it is if you memorize what I told you, which is when you have an increased amount of B field going in, to oppose that, you need to have an increased amount going out. And whenever the last thing you say is out, it's counterclockwise. So you can kind of memorize it or just think about it. I'm going to pause here because it's kind of like the most important part of this question. The rest of it is gravy. This part. Okay, so we've now established that our induced current, that's right, I induced, is going counterclockwise. So for part B, we have an answer. Counterclockwise. And all right, just to be clear, so we have the situation where we want to impose the change in magnetic field, right? So we have, as this bar moves more this way, there's going to be more B field going in, right? So like, imagine this bar is now over here, and along this path, there's a bunch of these B fields. There's going to be more going in, so we need to have more going out. So we use right-hand rule number 2, put our thumb at any point, and we know the only way to have B field coming out is if we're going counterclockwise, right? No matter where you are with respect to this loop area, your fingers can only point out if you're moving in a counterclockwise induced current. Sorry. And if your fingers were pointing into the page, that'd be going clockwise. So that's the idea of it. Okay. And we're asked then to solve in part 2, what is the magnitude of the induced EMF? Well, we have a motional EMF situation. So we have a particular equation whenever we have an increasing or decreasing magnetic flux in the shape of a rectangular square, right? Motional, sorry, I don't know why I wrote part B here. It's part A. Motional EMF, that tells us we're going to be using the induced EMF is equal to BLV, right? And what was B was 0.5, L was 0.5, and the velocity it's moving was 2. So it's going to be 0.5 times 0.5 times 2, and it equals 0.5 volts. That's our E induced. Okay, and then in part C, or part C, we wanted to see what the current in the circuit is. So we can use a modification of Ohm's law. We remember that V equals IR. So as applied in this situation, we can have E induced is equal to I induced times the total resistance. We're already told what the total resistance is. We can easily rearrange this to solve for I induced. That comes out to be 0.25 amps. And then the last thing what force must be applied such that the rod maintains a constant velocity. Okay, so if you imagine doing right-hand rule number 1, pointer finger the direction of current going through the rod up, middle finger going the direction into the page for B field. Our thumb is pointing leftwards, so that means the contribution now of magnetic force is pointing leftwards. So we're going to need a force going to the right to keep it at equilibrium there. So we'll call that F. And now if you remember, F equals ma, so part D, F net in the x direction, both of the forces are in the x direction, is equal to max. We're talking about constant velocity here. Acceleration is equal to 0. What are all the forces in the x direction? F is equal to minus fb is equal to 0. So you can now solve for F, which is the force of interest right here, and is going to be equal to FB. What's FB equal to? That's going to be equal to I induced L cross B, cross product. That tells us to think sine the angle between the field and the length here. So it's going to be like going like this. And then, I mean, that's extra, but it's equal to 90 degrees. So sine 90 is equal to 1. So you don't even need to worry about it. We already just solved for I induced. That's 0.25. L, that was something that was given. B, that was something that was given. You can solve for F as is equal to 0.0625 newtons. And in which direction? Rightwards, for the reasons we've already talked about. Sorry, that whole thing about cross product is not something we really need to worry about. Same thing with dot product. I think that, yeah, don't know. Okay, so here's an LRC question. In our last SI sheet, I think it was the last one, maybe 2 ago, we also did a good LRC type question. But this is the like the AC LRC situation here. And it's just this like series of equations. We just got to know how to use them. So we have this LRC circuit. They give you a bunch of the values that constitute this guy. We need to first find the impedance. We need to then find I max. Also I naught and I max. Those are, you can say that either thing means the same thing. We want to determine the peak voltage through each element. And we want to determine the phase angle. And the phase angle tells us if the current lags or leads behind the voltage. More on that in a sec. And we're going to determine the average power dissipated in this circuit. Okay, so let's draw this guy out. So this is Q4. Let's see. It's just like someone asked why I naught equals I max. It's just like a naming thing. I don't know. That's it. So we want to first define impedance. And impedance is basically the total resistance of this entire thing, right? So in our little diagram, we have an inductor, we have a capacitor, and we have a resistor. But let's first find the impedance, which is the total resistance of this circuit. So the first thing we need to do is to calculate the inductive reactance and the capacitive reactance, right? XL or XC. So let me zoom in my notes. So this right here. Let's find that inductive reactance, or XL. So XL is going to be equal to 2 pi that frequency times L. In this case, that comes out to be equal to 56.6 ohms. And then we have XC here, which is equal to 1 over 2 pi F, and the capacitance, that equals 39.8 ohms. Everything's coming out in terms of ohms. So that again makes sense on why our impedance here is equal to the total resistance. We know R squared plus, and then we just add those two things we just solved for together, square Z, that equals 200.7 ohms, again, in units of resistance. So that's part A. Part B, we want to find I max. What is I max is equal to? Well, modification on Ohm's law is equal to V max over the impedance, the total resistance. And you just plug in everything and you get 0.24. Okay. Next thing, we want to determine the peak voltage across each circuit element. So this requires us to know I max, right? Because the max current tells us the peak voltage at each of these situations. So we have V max at the resistor is equal to I max times R. We have V max at the inductor again, that's equal to I max times the inductive reactance, which is XL. And we have V max C, which is equal to I max times the capacitive reactance, which is that XC. Okay, and then plug everything in. That comes out to be 48 volts. This comes out to be 13.6 volts. And lastly, this comes out to be equal to 9.6 volts. Okay, part D. Oh, let's see. Yeah, so I naught is equal to I max. That's that first question. And then we're asked for the impedance equation. Oh, thank you, Sam, for catching that. This is a minus sign right here. And we found I max using V max over Z. Okay, and then in part D, we want to find the phase angle. Phase angle is going to be equal. And when you find phase angle, there's a few different ways to do it. I like to use the tan function because that tells you lags or leads. And they don't often ask for it, but you know, if like in the off chance they do, you might as well be able to hit what could be a potentially 3V type situation. So I'll tell you what that means in a sec. Here's our equation for phase angle. Phase angle equals 4.8 degrees. Okay. And you know, these are like sine waves here. They gave us V max, right? Yeah, it's in the question. So sorry, I lost my train of thought. So yeah, the phase angle. So using the tan function, it actually tells you if you lag or lead. So if your phase angle, that means this thing, is greater than 0, that means your current lags behind the voltage. And then the inverse is if your phase angle is less than 0, that means your current leads ahead of the voltage. And these are these these are these waves, right? And basically what that means is your current will reach I max in the case that you're lagging. That means your current reaches I max after the voltage reaches I max. And in the case your phase angle is less than 0, your current leads ahead of the voltage. Basically, your current will reach I max before your voltage reaches I max. It's just kind of a wording thing. And you can also solve for phase angle using cosine. I don't even remember the equation for that. But the problem is using that methodology is it doesn't tell you lags or leads. So that's why I prefer this one. And then we're asked to solve for the average power dissipated in the circuit. So P average, you know, we have a lot of questions, we have a lot of equations for average power or for power in general, but here we're dealing with P average. So P average is equal to I RMS squared times R, where that RMS is going to be equal to I max divided by √2. We already know what I max is equal to, so we can just solve for P average is equal to I max over √2 squared times R, and that comes out to be equal to 5.76 watts. Okay, let's see. Oh, the positive phase angle lags. Current lags behind the voltage. And okay, a lot of people are confused on where we got V max. That naught symbol tells it's the max, right? So we're told V naught, so that's 48 is what you plug in. 48 divided by 200. Yeah.
Sam, you have a question about the P average?
Mm-hmm.
Yeah, so I think on some of the practice exams, when it's asking for P average, it has like 1/2 I naught, like I naught square R, because like instead of using IRMS. So which one are we supposed to use?
Well, there's a lot of like different power equations, right? There's P equals IV, P equals I squared over R, P equals V squared over R. And then with respect to P average, there's like, you can use IRMS times VRMS, IRMS squared times R, VRMS squared divided by R, and then P max divided by 2 is also equal to P average. So it kind of what you have is what you plug in.
So would they all result in the same like answer?
Well, like here we were able to, like, which other one could you use? Like, you wouldn't want to use, like the reason I chose this one here is because we knew what I max was, and we know we already were given R. So it makes most sense to use this one versus something that requires VRMS because we didn't solve for VRMS of this. You know what I mean?
Right, because but like in one of the practice exam, I think it asked for p average, and it
Mhm.
just did like 1/2, like I max squared r. So it just had the 1/2 because like I think in the sign, like equation, p average is just like 1/2 or something. So it just did 1/2, and then
Well, P
you
average is
like
equal to 1/2 P max. Is that what you're saying? And you solve for P max first, and maybe that's what they did?
uh oh, I can check that again, but okay, I think I got it. Yeah.
Okay. Yeah, or we can talk about it, or you can show me which one you're talking about. Okay. All right, let's keep moving. I want to hit. Oh gosh, that was the whole time I was recording. Try to stop the recordings when I answer questions. Q5. I don't know why I keep writing it in subscript. Q5. So we have a light incident on an equilateral triangle, glass triangle prism with a 45-degree angle. That's how the light enters on one side. We want to calculate the angle at which the light emerges from the opposite side. So equilateral triangle, every side is equal to 60 degrees. That was a nice one right there. Good triangle. Here we have this situation. 60 degrees, 60 degrees. And we have this light ray coming in at a 45-degree angle, okay? And the key thing here is drawing in the normal. The normal is always going to be perpendicular to the surface the ray enters, right? So we have this 90 degrees right here, right? And that's very important because when we use Snell's law, and we have n air, which is out here, which is equal to 1, and the n of the glass is equal to 1.54. And that normal is super important because it's the angle we plug into Snell's law. So we're told 45-degree angles, theta 1 to be equal to 45. That is where the angle is, right? Be very careful. It's not this angle. It is not that guy. It's the one that touches the normal. So by that same logic, we have this ray continue through this prism. The Snell's law is index of refraction sine an angle is equal to index of refraction sine the angle at which it exits, right? That exit angle is the one that touches the normal. You always touch the normal. So remember that. So it's not this one here. No, it's the one when you're touching the normal. So that's theta 2. And these ones are, once you set up the drawing, really just nice time with just working this guy out. So then you can solve for theta 2 because, sorry, theta 2, which is equal to sine inverse NA over NG sine theta 1, theta 2 is equal to 27.3 degrees. Okay, so 27.3 degrees. And then we know that angle now, theta 2, but we need to find how it exits. So again, we're going to draw a normal, which is perpendicular to the surface in which the ray is interacting, and then an exit vector. So what we're looking for is this angle right here. And I'll call that theta 6. And that's just because I know how many angles it's going to take me to get there. But theta 6 is what we're looking for. That's our exit angle. But we need to first find this angle over here to be able to plug into Snell's law. So how we can do that is just with some trick. So we can call this theta 3, and we know the relationship between theta. We can solve for theta 3 because we know that it's a right angle right here. Remember, the normal is always perpendicular to the surface. So we'll say part 2 of this is going to be 90 minus theta 2 is going to be equal to theta 3. Theta 3 is equal to 62.2 degrees. And now we have enough to solve for theta 4 right here because sorry, that's my bad. 4, because we have a triangle right here, 180 degrees. Triangle must always be equal to 180 degrees. So in part 3, we'll say that 60 plus theta 3 plus theta 4 is equal to 180. Well, now what we have to do, we know what theta 3 is. We just solve for that. So we get theta 4 on one side. Theta 4 is equal to 57.8 degrees. Okay, so we know theta 4. We can now solve for the angle that we need. We'll call that theta 5, because again, this is a right angle here. So part 4, 90 minus theta 4 is equal to theta 5. And theta 5 is equal to 32.2 degrees. We can now use Snell's law. Oops. We're now in the glass. Sine theta 5 is equal to, when we get into the air, sine theta 6, which is what we're looking for. Theta 6 is equal to 56.3 degrees. Okay, so this one is kind of the other way they ask this kind of question. You know, this is basically the same question that was on your homework last week that we had a question on. But I still think it's good just to see the setup here. So we see that a detective is like looking in a pool. He holds his light 1.3 meters above the water, and the water has an index refraction of 1.33. And it's the way the distance the ray enters the water is 2.5 meters from his foot at the edge of the pool. And then we want to know where in the 2.1 meter deep pool will we see the ray. So what does this situation look like? We have, you know, the ledge, and this is our pool. Got some water. And from height, we'll call this height 1, right? That's where the flashlight's being held. It's entering the water like this. And remember, we always want to be perpendicular to the surface with the normal. And it goes something like this, right? And we know the pool is, call this height 2, which is 2.1 meters deep. And from here to the normal, it is 2.5 meters. But what we're looking for is this distance right here. We'll call this d. So essentially, this is going to be the length 1, which is equal to L1, plus d is equal to L2. Okay, so we kind of have our setup here. We have air, we have H2O, which is equal to 1.33. This is equal to 1. Okay, and the first thing we need to do is to get that angle right here, because it's the one that's touching the normal. So we'll call that theta 1. And we're going to be looking for, we need to find theta 2 to then find d, and then to add d to L1 to solve for L2. So what's theta 1 equal to? Well, we know that these are the same angles, right? And then if you imagine, it's the same triangle. This triangle right here is the same thing as this triangle up here. So you can solve for that angle, theta 1, through using a tan function. Tan theta 1 is equal to L1 divided by H1. You know, it's an opposite over adjacent situation. And theta 1 is equal to 62.5 degrees. And we can now use Snell's law to solve for theta 2. In air, sine theta 1 is equal to n and H2O sine theta 2. Our theta 2 comes out to be equal to 41.83 degrees. Okay. And then using that 41.83 degrees, we can solve for d, because we remember that using a tan function, we can say tan theta 2 is going to be equal to d over H2. And that means d is equal to H2 tan theta 2. Now, when we want to solve for L2, which is for the distance from the detective to the where the light is in the pool, we're going to say L2 is equal to L1, which is that 2.5 plus H2 tan theta 2, which is just that expression or the substitution for D. L2 comes out to be 4.38 meters. Okay. So this last question, changing up the wording a little bit. A layer of juice covers an unknown material. A light ray travels upwards as shown. The index of refraction of juice is 1.33. We want to determine the index of refraction of that unknown material in part A. And we want to determine the angle the light makes when it with the normal in the air. So after exiting the juice. So let's draw this out. We have a situation where we have our air, we have our juice, we have our unknown. So we'll call this up here NA, call this NJ for juice, and then here we'll say NM for unknown material. Okay, we don't know what this one is equal to. We know this is equal to 1.33. We know in air it's equal to 1. And they tell us a few things. They tell us the angles with, oh wow, this one's tricky. They don't tell you with respect to the normal for that bottom one. So remember, we're perpendicular to our surface. We have our ray go like this, and our ray go like this. Okay, and here, look at this. Look how tricky they are. They give you 65 degrees. That right there is the trick play. Do not fall for it. You need to always be, your angle always needs to be touching the normal. So you can't plug in that 65 into Snell's law. You need to plug in theta 1. And theta 1 is going to be equal to 90 minus 65. Ooh, they tried to get us. 25 degrees. So yeah, don't mess that up or you'll feel really silly about that. That's like a quick way to ruin what could have been a pretty easy points. And then now we have enough to solve for the index of refraction of that unknown. So we'll say NM is equal to, sine theta 1 is equal to the N juice sine theta 2, where theta 2 is that 45 degrees. Then NM is going to be equal to NH2O sine 45 divided by sine, sine theta 1, which was what we just solved for. So at 25 degrees, and M is equal to 2.23. Okay, there's no units on that. And then we're asked in part B here, determine the final angle at which the ray exits. So let's do it like this. We'll call this let's put our angle symbol like that. So we're looking for that angle. Okay, now, oh, wow, this one's actually a tricky question, not because of the physics, but because of the because it makes you remember some math stuff. So we don't really know how to find any of the angles that are over here, other than the fact this is a right triangle. We already know this is 45 degrees. So by definition, this is also 45 degrees. So what we call theta, what was that, theta 2? Yeah, theta 2. And then that means this one has to be theta 2 also, right? Because, you know, it's a right 45 degrees, it's a right triangle. I'm sorry, right angle there. So the other one has to be 45. So that means in part B, when we're solving for the exit angle, we'll say N of the juice is equal to sine theta 2 equals N in air sine the angle we're looking for. And at this point, we should know how to plug everything in. And that exit angle is equal to 70.13 degrees. Okay. So any questions on that? So basically we have this drawing here where we have a metal rod of mass M. It's sliding down this frictionless ramp containing a magnetic field. The ramp is inclined at some angle with respect to the ground, and there's a uniform magnetic B that's pointing upwards. It's perpendicular to the ground over the entire region with which the bar moves. So assuming constant speed, let's find V. So I think it's kind of good to draw this diagram both ways, that being from like kind of like an angled aerial view and then a cross section. So let's call this B for bonus. And what I mean by that is like how it's presented here. We basically have this rod like this, and it's rolling down the hill. We know its length, and there is perpendicular to the ground. So that means it's like pointing straight up, some B field, right? So it's coming out of the page. Well, we're going to be having less B field coming out of the page as the rod closes this loop into a smaller and smaller space. So by Lenz's law, to oppose that change, we're going to want to have to increase the amount of B field coming out. So the only way to have out is going to be going counterclockwise, right? So our I induced will be going counterclockwise. And you can just imagine that, like putting your right hand rule number 2 and seeing that. Okay. And now the first, and then like I said, we're gonna also want to, well, I guess we can just start solving for the EMF. So what's our E induced equation? Well, E induced is equal to minus plus E divided by delta T. And we remember that what that negative sign really means is like increasing or decreasing. So, and we're going to substitute in B a cosine theta, right? And when we do that, we'll see we have delta B a cosine theta. But what's changing, right? Well, the field's not changing. The actual area is what's changing over time, for that matter. So when we rewrite this, we can now pull out that B cosine theta. And what's changing is that area over time. Okay, we have a change in area over time. And what's the area equal to? Well, it's going to be L times, you can say anything else. Oh, let's just call it X, the other side X. It is the distance that it is getting shortened by. So Lx. Well, the length isn't changing, it's the X that's changing. So now we can rewrite this. Oh gosh, I always do this with this question. This is how you derive the motional EMF equation. Dude, I always do that with this question because I forget that they tell us that. So we remember that the E induced when we're dealing with these moving situations is equal to BLV, and it's a dot product, but don't worry about that. So it's cosine theta, right? And what's E induced equal to? I induced R. Okay, so what we need to plug in eventually is going to be that I induced R. But for now, this is as far as we can go with this setup. This is where we end. Sorry, I always forget that we know the motional EMF equation. I don't know why I always try to derive it when I solve this one. So we're looking for a terminal velocity v. So that means acceleration is equal to 0. But to do that, we're going to need to know all the forces that are acting here. Well, when we want to draw all the forces here, especially with something that has a normal force, we should kind of draw the cross section. So let's draw the cross section. We have our ramp here, and we have this rod rolling down the ramp. It's a circle. Our rod's rolling down the ramp. And what we also have is this B field that is perpendicular, right? It's to the ground. It's pointing straight up, like this. Okay, so what are all of our forces here? Well, we have the weight of the object. We have the normal force. Now this should be looking like 135B. And we have FB. So how do we know the direction of FB? Well, we're going to do that right-hand rule we talked about. Finger direction of current, pointing the direction of field, which is coming out of the page, and our thumb is pointing to the right. So with respect to this, it's going to be going to the right. Okay. And we want to find everything in the X direction because that's the only way the velocity is changing. And we can see that is if we put our coordinate system on an angle, we'll only need to worry about what's acting in the X direction. But to first do that, we need to break things into components now. So we have FB like this. And then also the mass or the force by gravity like this. And we have a few angles that are theta. So this is theta. Remember, this is theta, and this is theta. Okay. So now we have enough to solve. So everything in the X direction, terminal velocity, acceleration equals to 0. What are our forces in the X direction? Well, we have the X component of the force of gravity, so mg sine theta, and then minus, we have FB and the cosine, or in the X component of FB, so FB cosine theta is equal to 0. Now we can move FB to one side. Like this. And what does FB equal? Equals I induced L E cosine theta. Oh, no, sorry, so that one's sine theta, but we don't even need to worry about okay, I'll write it here, but it's perpendicular, so it'll be equal to 1. Okay, so now this is where that I induced comes in. So we can now rearrange this equation to get I induced for a substitution just by dividing both sides by R. And now we can plug in I induced, right? So we plug in I induced. What we get is PLV cosine theta L and then B. Wait, this is oh, no, okay, that makes sense. Yeah, because the cosine theta from here continues on to down here. Okay, so then cosine theta. I know it should be cosine squared. And then divided by R. So now all you have to do is get all the squared values, B squared, L squared, cosine squared, V divided by R. Okay, and all that equals mg sine theta. So now you want to get V on one side, so you have to just divide everything, clean things up. V is equal to mgr sine theta divided by B squared L squared cosine squared theta. Make sure you put your squared in the right spot for cosine. And that's why I said like this one's bonus because it's kind of a little bit more difficult than kind of what I would say to expect. Okay.